So I'm going to talk now about the new computational theories of autism that actually state of what could be wrong at this very, very low level on the left, on the perceptual level, or actually on the level of information processing. And these are, since we're in the computational psychiatry course, these are computational theories, and they are based on the level of, or on the level of information processing, and are based in the computational framework of cognition. And again, we can't see the head here on this picture. I have actually changed it again. Or can you see the head here? No, you can't. Sorry. I have changed the other pictures, and I thought you could see it. So you have to imagine the profile of a head here. And so here are the eyes, here is the nose, here is the mouth, and you see all these sensory inputs you get through these channels, and here is the ear, you get sound. So you have all the exteroceptive channels that send you signals, inputs. We also have interoceptive channels from the body that send you inputs. And then we have the brain that is doing something, as we have learned, it's computation. So we are changing a set of inputs to a set of outputs, and these outputs could either be action, so doing something with the world and changing whatever signals come in next, or learning something about them, understanding something. I think it doesn't really help, sorry. But you're smart enough to imagine this head here. And the other thing is, as I said, learning, as we will see, changes also something about what you do. It doesn't really change something about what signals come in next, but what you do about the signals that come in next. So that's the context of the Bayesian brain. And I really touch on this quite briefly now because Rike will talk about it in great detail tomorrow and will do it much more skillful than I am able to do it. But I just give you a rough introduction. So if you imagine, again, so here you see now, it's the same head, but here it's with an outline. So you're exposed to an environment that sends a signal, and that you with your senses, you can kind of grasp them or projections of them, causing a sensation in your head, which is just a noisy projection of these data. And what is actually the task of your brain is to guess what's the most likely cause in the external world, or actually in your body, that causes these noisy signals that you get here. And we assume that the brain does this by having a prior belief about what it expects from the environment, and by a combination of these two inputs here, so the sensation, the noisy sensation, and the prior belief, it can compute the posterior belief, or what we call the posterior belief, which is the most likely cause behind the sensory input. And this can be mathematically described by Bayes' theorem, and you will hear all the details tomorrow. But kind of the basic idea behind is that actually our brain is an inference machine that always tries to compute the most likely cause in the environment or our own body behind these noisy signals that the brain gets all the time. And now, as I said, learning is one of the actions that can occur, or is one of the outputs that can happen when you get some inputs. And we have the same situation. So we have a prior belief about the world, and we have this noisy sensation. And there is a difference, and this difference we call prediction error. We have heard of that as well. And now is the problem. Not all prediction errors are informative. There's much going on in the world, causing constantly kind of signals of something has changed, something is different, but most of them we just have to disregard them, not get distracted by them. But how does our brain distinguish between what is important and what do we have to attend to and what do we have to disregard? So should we ignore the prediction error? Should we update our model? And how can we do that? So here comes precision into play, and we assume that the relative precision of the two sources of data, so the prior belief on one hand and the sensory data on the other hand, kind of decides on about if we attend to this new sensation or if we integrate this new sensation into our internal belief or if we disregard it. And one example is if we have a quite sharp prior belief. So we have a quite good idea of what's going on, of what we are expecting, what's happening here. And we have some noisy data, which are much more noisy than our prior belief is sharp. Then usually we don't really update our inner model. Our posterior belief will stay quite close to our prior belief. So we know what's going on. Something is happening. We don't really look at that. We think, I still know what's going on. The other situation is that we don't really have a clue what's going on. So we're entering a new situation, don't really know where we are, what things are. And we have a sensation which might be noisy as well, but much less noisy than our inner belief is noisy. And so therefore, it's the difference here between the prior belief and the sensation is the same. So the prediction error size is the same. But due to this shift in the relative precision, in this case, our posterior belief will be very close to the sensory input. So imagine you enter a room, you have no idea what's going on, you see a strange situation. Your next belief about what's going on in this room will be very close to what you have seen, i.e. a strange situation, and you would not have expected that before. So even if you have the same difference in what you expect and what you perceive or what you sense, depending on the precision you attribute to these two sources, the outcome will be different. And now we assume that in our brain this is organized, this type of learning and integrating information into the model of the world that we have in our head is organized in a hierarchical way. That on the very low levels, in the primary sensory areas, we have representation or beliefs about the here and now of this sensory channel that is representing in quite great detail what's actually coming on in here. And in higher levels, we have more abstract information or information that is kind of covering more of the senses and is getting more and more abstract and not covering only the here and now, but also larger temporal or spatial scales about the structure behind things that happen, about temporal evolution of things, etc. And the thing that's going on, but we assume is always the same. So we have a prediction from top down. If there is a prediction error which is attributed some significance to, the prediction error gets signaled to this higher level, and the model is updated, and this goes on in all areas. And if this runs smoothly and the significance you attribute to the things that you integrate into your model is good or well chosen, then this model can mature quite well and will give you a quite good representation of what actually is going on and will inform you well about what is going to be expected over time and over space, and will be able to explain away a lot of things and give you a good feeling of, I'm prepared, I know what's going on, I'll be able to react to that. So that was what is hopefully going on in all of your minds and kind of what guides us through life. Now, the Bayesian theories of autism spectrum disorders focus now on all these functions. And they assume that these high levels of abstract information that inform us well and guide us through life and guide us through new situations and inform us about what is to be expected are not well developed in autistic individuals. And that their main focus of how they explain the world is on the lower areas of information processes, or the more on the sensory areas, that they have a well-established representation of the here and now in very, very great detail, but have a little clue about how things are going to develop and what's the reason or the structure behind it. And what we think today, how this can come about, is that there is, due to probably many, many different reasons in different individuals, this balance of the relative precision or of the precision ratio of the sensation and the prior belief, either due to a very, very flat prior beliefs and kind of normal precision of sensation, or to very sharp sensations compared to a normal precise prior belief. However, in both cases, we assume that posterior beliefs or kind of the perception of the world is very close to the actual sensory input and shows little guidance through prior belief if it's sharp or not, but just the relative precision might be the problem. This leads to a constant change or constant signaling of prediction errors, which are signaled upwards and lead to a constant update of your inner model, an overfitting. And if you're doing that on the levels here, then you will never be able to actually grasp the really informative information about the larger dynamics. And these levels will never really mature because you have an overfitted model down here. So these are newer ideas of what could actually be the core problem of autistic information processing and behind all the symptoms that we will just look at once again. So how could this explain the different difficult autistic perception? So if you don't have these higher model levels, if you have weakly established abstract representations, you are not well guided in the whole space of sensations of where to put your attention to, of where something informative is going on, and you will be distracted by all these small variations that are constantly ongoing. And especially social stimuli show a huge amount of constant irrelevant variations. Just think about how you look every day. You look completely different every day. If I see you tomorrow, you all might have changed something on your clothes. Some might have different hairdo, some might have lipstick or not, or some might have their contact lenses and no glasses. So just from the visual impression, you might look completely different, but of course, if you look in the mirror, you will recognize yourself, and all your peers will recognize yourself, because some aspects stay the same or stay constant. But you will have to know on which aspects to focus to realize, well, these are the important aspects and they are the same, so it's the same person. So if you're not autistic, you don't have a problem with that. If you're autistic, your models might not guide your visual attention well enough to focus on those aspects that might be informative, i.e. show which identity this person carries, and you might be distracted by all this irrelevant stuff and probably not recognize the person. So this type of kind of sampling irrelevant information makes it difficult to extract meaningful information because you get stuck into irrelevant formal aspects, which leads again to overfitting and kind of impairs the maturation of these higher model levels, which could be seen as a vicious circle somehow. Then autistic repetitive behavior, another domain of symptoms. If you now structure your environment very well, like what is where, what is going to happen when, and everything is repeated every day in the same way, and you have explicit information about everything, then you don't need high model levels. Oh, again here the head is missing. Damn, I really changed this and it didn't work. So again, you have here, was it? Oh yes. Because, you know, my prior belief about this head is so precise that I don't even realize that it's not there anymore. It's almost delusional. You see it. Okay, well, your prior belief is quite precise as well. So it's a folie à deux. Probably have a folie à famille if there are other people around knowing these slides. So again, this is the head. This head is looking in this direction now because this has moved away from all the unpredictable environmental prediction errors, because he's in his environment, which is very precise, very predictable. Everything is known. All the dynamics are known because there are no dynamics. This is the optimal autistic environment. And then there are no prediction errors, no stress. You don't need high-level models to understand it. You function perfectly well. So this is one thing that Tony Attwood, a famous expert in autism, once said, autism is one of the psychiatric disorders you can cure immediately. You just put the person in his known environment, you close the door, don't disturb him, he will be fine, have no problems. So that's a bit what this slide symbolizes. That autistic repetitive behavior, doing always the same thing in a known way, is actually a coping strategy rather than a real symptom. I mean, of course you can call it symptom, but it's a coping strategy of dealing with the chaos of life that they usually experience in the outer world. Now, social interactions, now again, you have the head here that you can't see, and this time it looks again in this direction, and you have the model levels over there. And if you look now at social interactions, especially if there are more people involved than one person, then there are so many dynamics going on and so many constant changing things that mostly are irrelevant to actually what you need to know about it, that it just gets too complicated for these persons, and you would need very, very high levels of your model representing beliefs about personalities in general, people in general, cultural information, but also kind of personality information about these single individuals that you have captured over long times and now know those people. And if you don't have those informations and just see what's going on and what everyone is saying, but probably not hearing what they actually are meaning by what they are saying, things get really complicated. And that's why autists, if they don't have these abstract informations present at hand to grasp the meaningful information going on here, they're just stressed and they are not able to interact smoothly to whatever is going on, because first of all, they don't really understand, and if they understand, they don't have the reflex of how to react on it. So I hope that I've shown you in this brief overview that there are